M3 lesson 11 entitled The Graph of a Function. So we have two outcomes. The first one is to understand that a set builder notation for the graph of a re-evaluated function. The second one is to develop techniques for graphing functions and relate the domain of a function to its graph. A lot of things we're going to look at in this one is going to be computer programming design based, as illustrated in this given box right here. And so it's kind of interesting to look at and neat to perceive how domain and ranges, or what may have been discussed to you a while back, is an input versus an output. And so we kind of look at those things: input, output, x, y, domain, and then range. And so when we look at this program, we look at the elements. The first thing we want to see says declare x to be integers, and that's important. So if we look at the idea or the focus of an integer, the first thing we want to note is that it is non-decimal. That's important for an integer. An integer can be positive or negative. That's okay. But we do not want it to be a decimal, so it really restricts us to things like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or its converses: -1, -2, -3, -4, -5, -6, and so forth. We would not include things like 6.2 or 7.3 or 1/4. Those would not be integers. So it's a very select set of information. If we look at the next line, it says for all x from 1 to 5. So that means they only want us to use for our domain 1, 2, 3, 4, and then 5. Only those integers, nothing in between 1 and 2 or in between 3 and 4, just 1, 2, 3, 4, and 5. And then they want us to take that information and they want us to print this information, which is our range or our output for those given pieces. So how did this work out? You know, the output for the program code is 2. So how do we know that that's 2? Because if we were to take our function or print 2 to the x, if we had 2 and we raise that to the first power, that's equal to 2. If we did our 2 to the second power, that's equal to our 4. If we did our 2 to the third power, that's equal to 8. Our 2 to the fourth power is 16. And our 2 to the fifth power, that led us to our 32. And so what you're going to be seeing in each of these examples in this particular video is what is it declared. In this one is declared integer. We're also going to see something declared as a real number, and we'll talk about that in a minute. They'll tell us in each one what are we working from. So from here it was 1 to 5, that was our domain. And then our output is to print or show 2 raised to the x value, or that would be our range, which was listed right there. So if we looked at exercise number 1, they say perform the instructions in the following programming code as if it were a computer and your paper were the computer's screen. So there's certain things we want to look at that's important to note. One of them is everything that's declared is integers and integers only. So 1, 2, 3, 4, 5, or -1, -2, -3, -4, so forth. It says they want us to work from all x's in between 2 and 8. So that means I know that my domain is 2, 3, 4, whoops, we skipped 1, 5, 6, 7, and then 8. They want us to print this information, the 2x plus 3. They want that to be our given range for each of the domain. So for each of these x values, one at a time, they want us to determine what would that y value be given that situation. So let's just say we start with 2. And so we said 2 times 2 plus 3. Because again, they want us to print 2 times x plus 3. Well, 2 times 2 is 4, and then plus 3, so we get a 7. If I look at the next one, we'll just do a few of these. If I had the 3, then I would do 2 times 3 plus 3, so 2 times 3 is 6. Then I add 3, and then we get 9. So you see the idea of what we're doing one at a time. So 2 times 4, and then plus 3, well, 2 times 4 is 8. We'll add 3, and then we'll get the 11. So then it continues to print these numbers out one at a time. So we have 11. If we continued on, the next answer would be 13, and then 15, and then 17, and then we'd stop at 19. So our final answers would again be 7, 9, 11, 13, 15, 17, and then 19. That would complete our 2, 3, 4, 5, 6, 7, 8 in the given domain. In exercise number 2, they give us another one. It says we can also build a set by appending ordered pairs. Perform the instructions of the following programming code. So again, let's just look and see what's in it, because that's where you're going to understand what to do. They tell us that we're focusing again only on integers. Only on integers. Then we're going to initialize our program G as this given set piece. And that's what this is right here. This output information down here at the bottom. They want us to fill in this blank. So they want us to work for the domain from everything from 2 to 8. And so again, our domain is 2, 3, 4, 5, 6, 7, and then 8. Now this time they're giving us a different instruction. They're saying to take this information and send it to G. Well, G was this piece right here. And then they want us to do the next X and print G. Now, we're not going to resolve all these, because if you have a keen eye, you're going to notice it's the exact same problem as last time. But the way that they want the computer program to print it is a little bit different. So they're saying 2 gave us 7, 3 gave us 9. Then that would mean that 4 gave us 11, 5 gave us 13, 6 gave us 15, 7 gave us 17, and then 8 gave us 19. Again, these are the same answers from last time, but the only thing that this program asked us to do was to write it as an ordered pair, as an X, comma, Y in each one. Here we just go through the same example again, just noting one thing, so we won't talk about this one but a minute. So here's our same declaration, here's our same G. Notice our X's are still from 2 to 8, and our plots are still the same plots, but this time they just want us to graph it. And so they're just illustrating here that we could take those exact same points and illustrate those points as dots on a graph. Dots on a graph, or points on a graph. Now we start to see one switch, and so I'll point out the switch and why. It changes it to the word real. Now, if we see the word real, that's going to include all numbers. We're including decimals and fractions and everything you can think of, not just integers, not just 1, 2, 3, 4, 5, but everything in between the 1s and the 2s and the 3s and the 4s and the 4s and the 5s and everything else. And so if we look at this same piece, they give us this function, 2x plus 3. I'll go back a slide to review. This is that same 2x plus 3 that's right here that we've been working with. So nothing different. But this time they want everything in between 2 and then 8. Not just 2, 3, 4, 5, 6, 7, 8, but 2.1, 2.2, 2.3, 2.4, or 2.01 or 2.001. They want everything. Now, here's the point of this. You cannot list all these numbers. There's too many. So we have to have a better way to represent what's happening. And so if they want us to represent this, and they want it to plot, well, last time our information and our pieces that we plotted and graphed were just individual dots. So for example, it was like 3 and then 7, or 2, 7, and then 3, 9, and then we had this value here. So the difference is between what we had last time, because these red dots were what we had last time, and I'll go back to that previous picture, there they are, versus what's happening this time, is because it includes everything, the real, then we're going to actually take and draw a line through the dots, because it's impossible for us to draw a dot for every single point, so we draw a line. And so it's going to exist in between 2 and then 8. So again, we'll just make a note, in terms of taking your test or assessment when your teacher assesses it coming up, you want to know for integer, you're focusing on points on the graph, your x, comma, y. If you see in your program that your teacher writes and it is prefixed by the declaration real, then you are going to connect the points to create a line. That is something you want to think about because it will make a difference between correct or incorrect. Exercise 3, we're going to take a look at this final program and note that this is real, this is our function, and we're going to use all the values in between -2 and then 3. They want us to plot these values on this given grid. So the numbers again that we're using is -2, -1, 0, 1, 2, and 3, but we want to emphasize that this is a real. That means we're going to connect the dots or have a function that goes all the way through to include all the potential points that are in there. So our function is x squared plus 1. So if I solve some of these and started to figure them out, if I said -2 squared, well, -2 squared is 4, and then 4 plus 1 is 5. Let's write a better 5 than that. -1 squared is 1, and then plus 1, so we get 2. 0 squared is 0, and then plus 1 is 1. 1 squared is 1, plus 1 is 2. 2 squared is 4, plus 1 is 5. And then 3 squared is 9, plus 1 is 10. So if we plot these coordinates, -2, 5, we have a point that's here. -1, 2 is here. 0, 1, 1, 2, 2, 5, and then 3, 10 is up here. Now again, our domain, which is important to note, our domain is between -2 and 3. That's everything in between -2 and 3, so this needs to be a connected line that's going to follow this curvature motion down to here and then come back up. Now I stop there because that's where my domain ends. And so then finally they say, what is the range? Well, my lowest range that I'm going to have is here, and it's going to extend all the way up to here. And so we will want to say in our given domain, our range is going to be from our lowest value, which is 1, all the way up to the value of 10.